Hey everyone, this is the final project presentation for KCP, a modification to TCP that improves fairness. My name is Sagar Patel and I was advised by Professor Ketan Patel. Before we talk about our project, let's get some background about how TCP works. So TCP is one of the most important protocols on the internet. It stands for Transmission Control Protocol, and TCP facilitates the transmission of a reliable, ordered, error-checked stream of bytes between two hosts on a network. Segments are transmitted by TCP to an underlying layer, that underlying layer here being the Internet Protocol, or IP. And the interesting thing is that TCP provides these properties of a reliable, ordered, error-checked stream of bytes, despite the fact that IP provides no guarantee of reliability, order of delivery, or errors in the payload. TCP achieves this reliability because every segment that is received is acknowledged to indicate that it was received. Order is maintained because every single byte is numbered with a sequence number, and the TCP header contains the sequence number. And finally, error correction is performed via a checksum in the TCP header. And one more point we will note here in transmission is that each host transmits one congestion window worth of data every round trip time. We'll see why this is relevant in a minute. Okay, so how can we have congestion in a network? Well, routers have a finite-sized buffer that they use to store packets for future transmission, and when this buffer becomes full, the router must drop the packet. So you can have congestion due to an overarching general pattern of congestion, or if you have some transient bursty traffic coming through. There are other cases where you can have congestion, or rather where packets can be dropped, and an example of that is a checksum error at the TCP, IP, or link layers. Well, for within a network, you're probably considering the IP and the link layer. And these checksum errors can occur due to noise within the signal of the underlying hardware or some other type of corruption, or you can also have just a random bit flip. You could also have bugs in the software that is running on these routers or switches or the endpoints that can cause all these packets to be dropped. One of the well-known problems with TCP's congestion control algorithm is that it penalizes links that have a longer RTT when compared to links with a shorter RTT. So for example, this diagram, the solid lines denote a fast link and the dotted lines denote a slow link. So if there was a connection between those two PCs at the top, there was one TCP flowing between them, and there was one TCP flow between the two PCs at the bottom that are using that dotted line link, then both of these flows share a common bottleneck link. Now, despite the fact that these two flows are the only two flows that are running, the solid line, or rather the fast link, the flow with the shorter RTT, will have a better throughput than the flow with the longer RTT. The reason being that TCP's congestion control algorithm is penalizing the flow with the longer RTT. Now, why does this occur? So flows with shorter RTTs, they can probe the network quicker than the flows with the longer RTTs. And by probing the network, I mean probing the network for additional bandwidth to determine whether the congestion window can be increased or not. So the longer RTT flows may not receive their fair share of bandwidth at the bottleneck. Now that we've gotten some background, let's talk about KCP. We just spoke about TCP, where it transmits C-wind worth of data every round trip time. C-wind or congestion window is what adjusts based on the network congestion. So a fixed size packet is transmitted with a varying frequency. If you want to increase your congestion window, thereby increasing your throughput, you would vary the frequency at which you're sending these fixed size packets. KCP, on the other hand, transmits a segment every millisecond. The size of the segment is what adjusts based on the network congestion. So there is a fixed frequency and there is a varying sized packet. This contrasts with TCP. What is the benefit of such a modification? Well, it seems that now flows with shorter RTTs don't have a significant advantage over longer RTT flows. We can now expect packets that are larger to be preferentially dropped instead of random drops for any TCP flow. So our hypothesis in this project is that KCP is fairer than TCP. And now, before we get to the experimentation and methodology, I'd like to acknowledge some prior work. This project is based on Professor Sagar Patel's idea. Myself and another student, Peter Gressens, have worked on this project on and off for about a year. However, I worked alone in completing the Comp 631 course project. To the best of our knowledge, no one has worked on this type of modification of TCP before, or anything similar.
For our experiments, we are using NS3, which is a discrete event network simulator. We have implemented KCP in NS3, and we are now going to run experiments with different workloads and topologies and different traffic models. We plan to benchmark NS3's default configuration of TCP against our own implementation of KCP. We implemented KCP as a drop-in replacement for TCP. We created corresponding classes, KCP Socket Base, KCP Factory, and KCP L4 Protocol. These names may sound familiar if you've been using NS3. At the moment, there is a slight caveat to our implementation in that KCP can only replace TCP on a node, and as a consequence, you cannot have both TCP and KCP sockets on a node. This is a pretty trivial problem arising from the fact that we want to use existing tools to look at packet traces. The problem is that TCP trace and TCP dump, two very well-known tools, expect a TCP protocol number inside the IP header. If you have a different number, these tools don't work. So we're just using the TCP protocol number for now. And in the future, if you want to run both TCP and KCP on the same socket, on the same node, you can simply assign both of them to different protocol numbers. In light of these issues with using other tools, we have developed our own custom data collection tools, data processing tools, and plotting infrastructure as well. In terms of our methodology, at the moment we are considering two different traffic models. We have infinite sources and we have a Poisson distribution traffic model. We're starting with a simple model of fairness right now, namely we count the number of bytes through a bottleneck for each TCP flow for every second. So every second time slice, count the number of bytes for each flow. And you can determine the average for every time slice across the flows, and you can also determine the standard deviation. A lower standard deviation for each time slice indicates that each node gets a more equal amount of throughput, which we are taking as to mean that that is more fair. Let's now discuss the Poisson distribution traffic model. The Poisson distribution has been used for quite a long time, and it's a relatively simple traffic model. The infinite source and infinite sink model that we're also using has a few drawbacks. Namely, it doesn't really accurately represent what traffic looks like on the internet. The hope is that the Poisson distribution can more accurately represent what this traffic is supposed to look like, namely more bursty traffic, more transient traffic. We will be using NS3's on-off application to implement this Poisson distribution, and the relevant parameters are the data rate, the on time, and the off time. So how the on-off application works is there are two states, the on state and the off state. When the application is in the on state, data is sent at the data rate, and when the application is in the off state, data is not sent at all. And the interesting thing about this application is that this on and off time can also actually be a random variable that follows a distribution. So we can have, for example, the on time follow a normal distribution or an exponential distribution or a constant distribution or a uniform distribution. And the off time can also be one of those distributions. Or it can also be a constant. So for the purposes of our experiment, I am using an on time as a constant 0.2 seconds and the off time as an exponential distribution with a parameter lambda equal to a half. If you remember from store 435, this corresponds to a mean of 2 seconds on the exponential distribution. Now, why are we doing this type of configuration? Well, it just so happens that with this type of configuration, you obtain a Poisson distribution in the events in the on events. So now the on events are independent of each other and they follow a Poisson distribution. This is because you can model the on events as a single point in time, they're constant in length, and the distance, or rather the time between two events, is modeled by this exponential distribution. This is how we obtain the Poisson distribution in the on events. We're using a standard dumbbell topology in our simulations. I've superimposed a few of the characteristics of our dumbbell, or properties, onto this image. Namely, the bottleneck link is 1 megabyte per second, and the leaves or the last mile links are 100 megabytes per second. All of the sources are on one side of the bottleneck, and all of the sinks are on the other side. Let's look at some final simulation details. Each source application starts randomly over some time period in the 0 to 5 interval. The simulation runs for a total of 100 seconds, and we will ignore the first 10 seconds of data. Why are we doing this? Well, not all of the applications are even running until the 5-second mark. And in the next we choose to ignore the next 5 seconds to remove any of the noise associated with TCP starting up. So there's the exponential increases at the beginning where TCP is trying to probe the network and determine what congestion window should be. And there's going to be some period where the congestion window and the throughput levels off. So we want to get all of that stable state information and ignore all of the noise in the beginning of the connection. We are now ready to look at some of the results that we have obtained. We'll look at the results from the infinite sources first. And just a note here, we used NS3's bulk send application. Let's take a look at our first example of an infinite source. In this simulation, there is a single TCP flow through the bottleneck. There is one sender and on one side of the bottleneck, and there is one receiver on the other side. And there's only one flow. Since there's only one flow, we can compute a mean throughput for that flow, but we can't compute a standard deviation, so it will be 0, of course. And here we show the plot of the mean throughput versus time for the KCP simulation and for the TCP simulation. So we see that the TCP simulation, TCP protocol is able to pretty much saturate the bottleneck link at about 1,000,000 bytes per second, whereas KCP is lagging behind a little bit. At approximately, if I eyeball this graph, 925,000 bytes per second, it's important to note here that the y-axis does not begin at 0, and we'll see that in the other plots that I'll be showing you today as well. Now, higher is better, so TCP is outperforming here, but is this a problem? We believe this is a non-realistic scenario because how often does it happen that a flow on the internet is a single flow on the internet is the only flow through a bottleneck link? This is an unlikely scenario for a large distributed network, so we will say that this throughput of KCP is an acceptable amount for now, and move on to the next experiment. In this experiment, we have 100 flows. There are 5 senders on one side of the bottleneck, and there are 5 senders on the other. Between each sender-receiver pair, there are 4 flows. Hence, we have a total of 100 TCP or KCP flows in each experiment. This plot shows the throughput versus time, and of course, since it's throughput, higher is better. And we notice that TCP is able to sustain and completely saturate the network, or the bottleneck link, pretty much at a constant 10,000 bytes per flow per second. Of course, this is an average, so this doesn't represent that each flow got the exactly 10,000. We'll see the next plot of the standard deviation. And we also see that KCP is able to saturate the bottleneck link reasonably well, not as well as compared to TCP though. Again, as previously noted, the y-axis does not begin at 0, so the lowest point here, we see that KCP saturates, or rather has a throughput of 9,700 bytes per flow per second. Continuing the same experiment, we're now plotting the standard deviation of throughput versus time. This is the same experiment with 100 flows, and in this plot, lower is better. We notice that KCP has a lower mean of standard deviation of throughput than TCP. And you can kind of eyeball the graph and see that TCP has significantly higher peaks in the standard deviation of throughput. So the standard deviation of throughput, if you will, is higher for TCP than it is for KCP. So that would indicate that TCP is a little bit less fair as well. Now that we've seen a few experiments with the infinite source model, let's take a look at the Poisson distribution traffic model. Again, I am using NS3's on-off application. In this experiment, we're using the Poisson traffic model with 100 flows. There are 5 senders on one side of the bottleneck and 5 receivers on the other. There's 4 flows per sender-receiver pair, so that gives you 5 times 5 times 4, or 100 flows in the entire simulation. Because this plot shows throughput, higher is better. Now, right off the bat, we see one difference between the infinite source model and the Poisson traffic model. We see that TCP's average throughput is not at the 10,000 bytes per second mark. And this is actually something we would expect. The Poisson traffic model doesn't necessarily saturate the link at all times. It is a bit more bursty. So there are times when we see the throughput of TCP and KCP reach 10,000 bytes per second. That is the bursty traffic. But we see that the average is approximately 9,700 bytes per second. And in this case, the throughput of both KCP and TCP is very similar. In fact, TCP's throughput and KCP's are essentially neck and neck. But let's see whether there's a difference in fairness. Does the standard deviation say a different story? For the same experiment, we have the standard deviation plot. Here, lower is better, and lower would imply more fair. And right off the bat, we see that KCP is fairer than TCP. In fact, it's even more surprising because TCP and KCP had a very, very similar throughput, but here we see that their standard deviations, the mean standard deviations, are quite different, and KCP is significantly fairer. I think this represents part of the benefits of using KCP over TCP. The last experiment we'll look at today uses the Poisson distribution traffic model, and what's different is that it will use varying RTTs. Again, as before, we have 5 senders on one side of the dumbbell, 5 on the other, 5 receivers on the other side. There's 4 flows per sender-receiver pair, giving us a total of 100 flows. Now, how do we achieve the varying RTTs? So recall that in a dumbbell simulation, there is a central link that is shared by all flows, and there are nodes that are attached with independent links to this bottleneck link. So what we've done is these last mile links, we are adding delays to them. And in particular, to each of the 5 links on each side, we are adding either a delay of 0, 0.1, 0.2, 0.3, or 0.4 milliseconds. So there's one link with each of these delays on either side of the dumbbell, and this is how we're achieving varying RTT flows. And now we'll take a look at the plot of the throughput. Again, higher is better, and we see that TCP is able to saturate the bottleneck link reasonably well. KCP does an okay job as well, but it also drops quite significantly at certain points in the simulation, and its average is lower than TCP's. Now let's take a look at the standard deviation. We see that the standard deviation of throughput for TCP is higher than that of KCP again, indicating that KCP is indeed fairer in this case as well. So we've seen several experiments where KCP's fairness is better than TCP's. So you may be wondering, why doesn't everyone just use KCP? Well, to start out, we've already seen several cases where TCP's throughput is higher than KCP's, so KCP is lagging behind in that respect. There's also another problem, and that occurs with high bandwidth connections. When you have a high bandwidth, you will have a low RTT. However, KCP can only transmit once every millisecond. You may correctly think that that's okay because KCP increases its packet size every millisecond, or it will increase its packet size if it wants to send more data. And that's correct, but you also need to consider that that packet must fit inside of the buffer that the routers use inside the network. And if the packet is too large, if it doesn't fit in the buffer, then the packet will be dropped. One of the straightforward solutions is to make the size of the buffer larger, but this could lead to buffer bloat. We will continue to investigate these issues, and here is the plot I was telling you about that shows the high bandwidth flow. This experiment is similar to all the previous ones, except that it has a higher bandwidth at the bottleneck link. In fact, it's 10 times faster, so the bottleneck link is now 10 megabytes per second, whereas in previous experiments it was 1 megabyte per second. We can see quite clearly that TCP's performance is significantly better than KCP's in terms of throughput. TCP is able to sustain and saturate the bottleneck link at about 100,000 bytes per second, and KCP is falling significantly behind at only 35,000 bytes per second. We are currently investigating these cases of high bandwidths. There is a chance that there is an error in my implementation, and there's also a chance that we can make a small fix or we can add some simple heuristics to fix this problem. We're also exploring how changing the size of the buffers in the network at the bottleneck link can affect the throughput of a KCP flow. While this project is complete for the purposes of Comp 631, it will continue in the future. Namely, we would like to implement even more realistic traffic models using NS3's 3GPP HTTP client server model. This is based on the 3GPP HTTP standard. In addition, we'd like to implement even more complex topologies. Right now, we've only seen dumbbell topologies. In the future, maybe we'd see star topologies, or possibly grid topologies, or any other type of topologies. Thank you for watching my presentation, and I look forward to your questions on Tuesday.